Hello and welcome to the tutorial on trigonometric exact values. In the past we've used things like sine, cos and tan to help us find angles and length of sides in a triangle. But whilst we've put in things like sine 45 degrees in our calculator and receive values of 0.071, etc, 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 we haven't really questioned about where these values came from. What we have noticed, perhaps, is that the values aren't exact. That is, the decimal goes on and on and on, way beyond what the calculator actually shows us itself. So, where did these values for sine of 45 come from in the first place? And what is the exact value, rather than the approximation given by the calculator? Well, today's tutorial hopefully will show us just where those values were determined. So to start with, I'm going to draw an isosceles triangle. Now my isosceles triangle is going to be right-angled, which means that these angles in here are going to be the same. We know that because isosceles triangles not only have two sides which are the same, but they also have two angles which are identical. And the only way for those angles to be identical is if they're 45 degrees. So that 45 plus the other 45 plus the right angle there gives us a total of 180 degrees for our triangle. For the purposes of this demonstration, I'm going to mark in the length of those sides as 1. And I'm going to use a bit of Pythagoras Theorem to help us find the missing length, this hypotenuse. So we'll just do that up here. So Pythagoras Theorem is written out, and as we know it's the short side squared plus the other short side squared, and added together. So that'll give us 2, but when we take the square root of that, the length of our hypotenuse can be shown to be root 2. So we'll mark it in on there. So how does that help us with our work on trigonometry? Well, let's have a look. If I was to take the sine of an angle, I know sine is given as opposite over hypotenuse. So specifically, if I was to look at sine of 45 degrees, which is what our triangle is actually showing us, we'd have a look and we'd say, okay, well that's the opposite of this particular angle. So I'll put it as 1. And the hypotenuse is the one we've just found, which is root 2. So sine of 45 degrees is 1 on root 2. Now that is what we know as an exact value. If I typed it into my calculator, lo and behold, it would come out as the value 0.7071, etc, etc. Exactly what we got over on this side of the screen when we started. Now, we can do similar things to help us find exact values for things like cos. So looking over here, we might try cos of 45 degrees. So cos we know is the adjacent, which is this side, over the hypotenuse. So again it's 1 over root 2. Adjacent over hypotenuse. So once more we can add this, or calculate this on our calculator, and we see that it's 0.07071, etc, etc. Not only is it identical to the sine 45 degrees we just found, but if we type in cos 45 degrees on the calculator and press equals, then we'll come up with this identical number. So let's add those numbers into our table that we've got down here. So the cos of 45 degrees, that exact value is 1 on root 2. And the sine of 45 degrees was also found to be 1 over root 2. There's only one left to do, and that's finding the tan of 45 degrees for this particular triangle. So over here we look at tan of 45 degrees, and tan we know is defined as the opposite side over the adjacent side. So our opposite side here is 1, and our adjacent is also 1. So that gives us a tan of 1 over 1, which is obviously just 1. So tan 45 degrees equals 1, and can be added to our absolute value table, or exact value table. Again, if you've got your calculator handy, you can type in tan 45 degrees, and you may not be surprised to see that it actually turns out to be 1. Okay, so let's continue on and see what we can find in terms of, say, sine, cos and tan of 30 and 60 degrees. I'll just give ourselves a bit more space here. So, to help with this one, what I'll do is I'll draw a second triangle. And this triangle is going to be an equilateral triangle. Now with equilateral triangles, as we know, all sides are the same, but also all angles are the same. And the only way for that to occur is if all angles are going to be 60 degrees. Now what I'm going to do with this one is actually divide it in two. So I'm going to draw a line right down the middle here. Let's redraw it over here and see what we've got. So here's our redrawn what was an equilateral triangle. Up here, and I should have mentioned before, if we allowed those sides to be 2 in value each, you might find then as we come down here, this side still remains 2. This side is only 1 because it is only half the length it previously was. And the angles in here will remain as 60 degrees, 30 degrees here, because once again it's halved, and this becomes a right angle. Using Pythagoras, it's possible to find that missing side. So Pythagoras' theorem can be written as c squared equals a squared plus b squared. But if we want to find one of the short sides, we'll rewrite it as a squared equals c squared minus b squared. C squared is our hypotenuse, so we'll square that, and we'll subtract from it the other short side that we know. So that'll be 4 take 1, which is 3. If we now find the square root of that, our missing side is the root 3. So I'll mark it in on our triangle here. Continuing on now, we can do what we did previously for finding the sine of a particular angle. So sine of 30 degrees, we know once again 30 degrees, which is marked in here, is going to be our opposite over our hypotenuse. So sine of 30 will be 1 over 2, or a half. I'll mark it in on our table. Cos of 30 can also be determined. Cos is adjacent over hypotenuse. Now our adjacent is this calculated value we've just found over our hypotenuse of 2. So cos of 30 would be the adjacent root 3 over the hypotenuse of 2. And once again, I'll mark that in. And finally, tan of 30 degrees can be determined. Now tan is when we've got the opposite side over the adjacent side. So in this case, it'll be 1 over root 3. And once more, we can add that in to our table. Continuing on, we're going to look now and reorientate ourselves with the triangle. We'll look at the 60 degree. So that now means that this becomes our opposite side. This becomes our adjacent, but our hypotenuse remains the same. So if I was to look at sine of 60 degrees, remembering that our opposite side is now root 3, we'll put opposite over our hypotenuse of 2, and that will give us the value that we need as an exact value. So I'll mark it in up here. Cos of 60 can once again be determined. Cos is our adjacent over our hypotenuse, so that will be 1 on 2, or just a half. Again, we can put that in. And finally, tan of 60 degrees is going to be our opposite, which is now the root 3 over our adjacent of 1. So root 3 over 1, or simply root 3. So again, that will go in here. The remaining values for the table will fill in at a different stage, but I think you can go and confirm that these values, if you type them into your calculator, will be the same whether you put in, say, root 3 for tan 60, or whether you type tan 60 itself. The numbers should be identical as they come up. Thanks very much. I hope this has helped.